Okay, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Larry Lemke, who's come across to us from NASA Ames. Larry did a Bachelor's of Physics at Portland State University, and then he did a ME in Aerospace Engineering at Stanford. And since January 1980, he's been affiliated with the Ames Research Center, where he's conducted a variety of innovative designs for aerospace vehicles, particularly for Mars. His career interests have revolved around conception and design and testing of aerospace vehicles in support of advanced space missions. And he's been involved in such projects as the Mars aeroplane concept, which was tested in 2001 with a prototype. He's also been involved in the Marte drilling project in Spain, and in the design for caching, for sample caching on Mars Science Laboratory and other missions. And he's also very interested in the idea of Mars sample return using commercial capabilities, which is what he's going to talk to us about today. So please join me in welcoming Larry.
Okay. To advance the slides, just the down arrow, is that the, okay. Thank you. I would also like to point out that in the audience I have two co-conspirators, Andy Gonzalez here, who's a senior engineer on the project, and Carol Stoker, who was the science PI on this set of studies. And they will keep me honest whenever if I say something that's not quite true. I invite them to feel free to pipe in and tell how it really is. Okay, so this set of activities, hi Dave, this set of activities got started a few years ago. Actually, I think it was 2010, if I recall correctly, and a group of us usual suspects were kind of hanging around the hallways of Building 245 over there, and as we tend to do, we tried to think of what would be the next sort of, disruptive space exploration technology. And one of our colleagues, John Karch, pointed out that the Dragon capsule that was at that time was announced and was being developed by the SpaceX Corporation had on it all of the subsystems, in theory at least, necessary to do an entry, descent, and a soft landing on planetary surfaces. In particular, of course, it was designed to do that on Earth. That is to say, the crew-carrying version of the Dragon capsule will be designed to do that on Earth. And so the question was raised, could you take the same system or a slightly modified version of that system and do the same thing on Mars? And so that's really kind of what set us off on this particular study. I'll point out that the answer to that question is not necessarily. I've been doing advanced space mission designs for 35 years, and every few years somebody comes up with the brilliant idea that we could take a spacecraft that was designed to operate near Earth and let's send it to some other planet and we can do great things for cheap. For example, communication satellites. If we can take a communication satellite that was designed to go around Earth and put it at Mars, maybe we could get a cheap, relay. And it almost never works out that when you sit down and do the actual detailed design, that's a good idea. It always ends up there's compromises somewhere along the line, and something that works well in one application doesn't work at all in another. And so we were frankly skeptical when this idea came up that you could take a capsule that was designed to operate at Earth for Earth return entry and do it at Mars. Nevertheless, over a couple of years of detailed study, we convinced ourselves that indeed that was true. And I'm going to go through some of the gory details about how we convinced ourselves of that. And so then the question became, well, okay, if you accept the basic premise that a Dragon capsule could be utilized to land on Mars possibly for the purpose of hosting robotic missions. It'd be a station on Mars that from which you could operate robotic missions. How well would it work? How much could you land? So that set us off, and we decided to take as a case study the Mars sample return problem. That being practically the most difficult upper end of the spectrum that you could hope to address, and to see whether or not we were within the range at which that might make sense. So that's basically what I'm going to talk about today, is a Mars sample return scenario that would utilize Red Dragon, or for that matter, I suppose, any other commercial capability that would come along with that kind of capability. But right now there's a population of one, so we'll focus on the Red Dragon. So we'll basically describe what a Mars sample return mission architecture would look like, and then we'll dig into a bit of the details as to why we've convinced ourselves, and others, I might add, that we think this is feasible. Okay, so here's the reference mission. This is what we are basically comparing ourselves to. This is the taxonomy of the mission that's described in the decadal survey, which basically says that the Mars sample return is the highest priority if you can do it within the agreed upon budget, and if you can make sure that the samples returned are of sufficient scientific merit that it would justify that. And so that's the challenge that's basically been laid down to the spacecraft engineering community. And you can see that it's a very complex architecture, and that is why it's perceived as expensive by almost anyone, and why there's also perceived to be a large cost risk, because NASA is not that terrific at staying within the budgets that we estimate as time goes on. But basically, the idea is you have 3 separate launches over 3 separate opportunities. The first one uses a Skycrane lander and deposits a rover whose function is to go out and obtain the samples and cache them. The idea being this ensures that you get high quality science samples. The next launch puts roughly the same amount of mass toward Mars, another Skycrane lander. It deposits a station with a launch tube on it. It launches a small rocket off the face of Mars. It has a small fetch rover that goes out and grabs the samples that were previously acquired, brings them back, puts them on this little rocket, goes up to Mars orbit, where it rendezvous with a spacecraft. Did I mention there was another launch, another Atlas V launch that got that orbiter to Mars. So this spacecraft has to perform an autonomous rendezvous with the sample, which is now in Mars orbit, and it's not really a cooperative target. It's really kind of a dumb piece of mass about the size of a basketball. It autonomously rendezvous with that, transfers the sample into an Earth entry vehicle. This rendezvous, the orbiter then does a burn out of Mars orbit, comes back to Earth. As it's approaching Earth, it ejects this Earth entry vehicle, which comes back down and does your standard ballistic entry with a parachute deployment, and is recovered in Utah or perhaps Australia or someplace. And that's basically the entire mission. It has been studied many times by various parties, industry, and other NASA centers that perhaps this is not the best way to do it. In particular, it has been pointed out that if you can, basically this requires 3 Atlas V class launches over a period of about 6 years, all of which have to work perfectly in order to get anything back. And it has been pointed out that if it were possible to launch, if you had bigger launch vehicles, if you could throw more toward Mars at a single go, that you could take all these functions and instead of aggregating, spreading them out over multiple missions, you can aggregate them together and maybe save some subsystems and make the whole thing simpler by being able to throw a bigger chunk all in one shot. In the past, people have looked at, for example, like the Space Launch System, or NASA has periodically had these Saturn V class launch vehicles. We call them different things at different times. Currently, it's the SLS. But the idea is, if you had 100 tons in Earth orbit, maybe you could use that capability to throw a big enough chunk of mass toward Mars that you could accomplish a sample return all in one shot, all in one launch. So our effort was to see how close we could get to that idea, to move in that direction. In particular, because the Falcon 9 Heavy is coming along, and it is not quite the SLS class, it's not quite the Saturn V, but it is a very, very substantial vehicle. It can throw about 10 metric tons or more, actually about 13 metric tons toward Mars. And so the question was, is that a big enough increment that it could possibly make this kind of an architecture possible? This is a recent photo from SpaceX showing the version 2 of their Dragon capsule that they just they pulled up the curtain on this one a few weeks ago, and this would form the basis for the landing vehicle that we're discussing. So our concept here is that you on one launch you launch a Falcon 9 Heavy with a modified capsule like this toward Mars. It cruises towards Mars. The capsule has this little cruise stage that provides thermal control and power and stuff like that en route. So before you get to Mars, you eject that. Then you do enter, descend, and land with your capsule. You're on Mars. The capsule contains in it an ascent stage, basically a 2-stage rocket that's capable of coming all the way back to Earth. On the surface, it has to rendezvous with a rover of some sort to get the sample to it. Now we're not studying that portion of it, so that function can be handled by something else, and quite possibly actually the 2020 rover that's currently out for competition. In any case, once the sample is on this Earth return vehicle, it comes straight back to Earth. It does not stop in Mars orbit. There's no Mars orbit rendezvous. And it comes back to Earth, and you have one of 2 options. One option is you capture into a very high Earth orbit and stay there until you send up another capsule to grab the sample and come home. And that other capsule could be any one of a number of options. It could be another crew capsule. It could be a Dragon capsule. It could be the Orion capsule if that's ready. It could be a robotic mission. We're agnostic on that, so there's a number of possibilities there. The other main branch of the architecture is that instead of going into Earth orbit, you actually just, again, come back and do a direct Earth entry with a small entry vehicle. We believe that the current technology that we're developing at Ames, as well as other places, would allow the construction of an entry vehicle that is light enough and small enough that you could actually do that. You could put it on this ascent vehicle, go all the way from Mars directly back to Earth and do an entry. So this would basically involve 2 Falcon Heavy launches, which we believe could be purchased commercially. That is to say, you would simply buy the service of delivering mass to Mars and back to Earth, as opposed to being heavily involved in the, in the development of process of procuring it in the regular sort of NASA manner. So we believe that that's actually one of the main rationales as to why we think this could be considerably cheaper than the way NASA would go about it.
What are the 2 launches?
Well, in this scenario, one launch is the one to Mars with the landing, and then after the sample has been acquired and stowed, you come back into Earth orbit. The second launch is a launch from Earth to that orbit. You rendezvous with the capsule in a near Earth orbit somewhere. Okay. Does not, as I said, it could be any one of a number of different options, depending.
And I have to say, full disclosure, when you start counting up the launches, then you'll see that there really are 3 launches. One would be the 2020 rover, but that's already booked. One would be to Mars, but the third does not go to Mars. It goes to Earth orbit. And there are commercial launches, therefore those 2 launches are much cheaper, we propose, than 2 Atlas V launches to Mars.
Okay, so when you sort of add up all of the bits and pieces that would be necessary to implement this, this is kind of what it looks like. First of all, there's the Falcon Heavy itself, of course, which is under development. The capsule, we're calling this the Red Dragon, of course. The capsule, the Dragon version that is modified to be able to land on Mars, we just coined the term Red Dragon. So that capsule itself needs to be developed, and it would be, as we say, a small modification of the existing SpaceX plan. Then the capsule in it has to have basically the Earth return stack, which we've shown conceptually here. It's basically a minimum of a 2-stage rocket that's sitting inside, for all practical purposes, the missile silo inside the thing. And so when the Dragon capsule lands, it's got the fully fueled Earth return stage in it, and there'll be a robotic arm that's capable of acquiring a sample from nearby, putting it into the capsule up here, and then returning the whole thing toward Earth. So then, as we say, you need another launch from Earth to go out and rendezvous with it. That could be a Falcon Heavy, or it could be something else. Okay, so, and as Andy mentioned, the potential exists for this to interface with the 2020 rover. Currently, it is not designed, it's not planned that this rover would interface with a scheme like this, but there are a lot of people on the rover team who are interested in this, interested in studying it, so that's a possibility that could be out there. Okay, so basically the issue was you have this set of stuff, this parts list that I just illustrated, that you basically have to cram into the capsule, and that set of stuff has to be able to go all the way from the surface of Mars all the way back to Earth orbit, has to be a fully capable deep space spacecraft, abiding by all of the NASA standards for reliability and redundancy and all that sort of stuff, and then modifications to the Dragon capsule itself, some of which would add weight, and so basically this is the stuff needed to get the sample back. And the question, and then the separate question is, well, how much mass and volume can the Red Dragon deliver to Mars? And hopefully, this will fit into that. That's basically the essence of the study was, does this pile of stuff fit into that? And to answer that question, we had to go into quite a bit of depth into both sides of this equation. We had to do a pretty detailed design of the Earth return vehicle and all the modifications that you would need for the Dragon capsule, and then we had to do a very thorough analysis of exactly how much we thought you could land on Mars, and then compare these two. So I'll turn first to the second part of that equation, the how much can you land, okay? So this is a discussion about the entry, descent, and landing, or as we like to say, EDL, which is basically the study of what happens when the capsule enters the Mars atmosphere, and can you calculate it all the way down to the Mars surface with a soft landing. So basically, it's traditionally EDL is broken into these phases. The first thing is the hypersonic entry. Now the probe comes in at high speeds that are basically determined entirely by the size of the solar system and the distance of the planets and so forth. And that velocity turns out to be somewhere around 6.5 kilometers per second, typically, to enter at Mars. A little bit less than what it is for an Earth orbital reentry, but kind of in that same range. And during that hypersonic phase, the trajectory of the capsule is determined entirely by the outer skin of the capsule just running into air molecules and pushing them out of the way and having the exchange of momentum. And if it does that long enough, it'll slow down and scrub off the excess velocity. Typically, for an object the size and the mass of a Dragon capsule, after it's done that, after it's scrubbed off this excess velocity coming in, it's still moving at supersonic velocities. It's still, even down at low speeds, the most that it's going to scrub off is going to still leave you going somewhere between Mach 2 and Mach 3 down near the surface. So if you did nothing else, you'd crash, and so you obviously have to do something else. And that something else starts happening at these low Mach number supersonic speeds. And so all of the missions that we've put to Mars, the NASA missions to Mars to date, have utilized a parachute at this point. Basically, after the entry capsule has scrubbed off as much of its excess cosmic velocity as it's going to, they pop a parachute, supersonic parachute, that typically slows from about around Mach 2 down to subsonic velocities, and it continues on down, descending under the parachute, and then in that last 500 meters or so, another miracle happens, and you either use airbags or you have some system to take out that last increment of velocity. So it could be airbags or soft landing rocket systems like Phoenix or like Viking did. And so those are basically the three phases of entry, descent, landing. And you have to be able to calculate your way through each of those and show that whatever it is you're proposing to do, that the equations close, for each of those. Oh, above ground level. Yeah. Okay, so when we first set out to address this, we got the usual blank stares and wild-eyed comments that how in the world could you possibly take a big, heavy, honking, manned capsule that was designed to operate on Earth and get it slowed down at Mars, because the Mars atmosphere is 100 times thinner than Earth's atmosphere, and I mean that just intuitively doesn't seem to really make sense. And so the skepticism we got is based on that. Well, so it's a little bit of a detailed answer, and I'm going to kind of go through the steps to hopefully convince you. First of all, let's look at what would happen if you had something that was not as big and heavy as a Dragon capsule. Let's say you look at some of the other missions that we've put there, like Mars Pathfinder or Phoenix and things like that. To first order, those do not involve any lift, any aerodynamic lift, so you can basically treat them as though it was just a ball. Just imagine a ball entering the top of the Mars atmosphere and ask yourself, you know, what would it do if as that ball gets heavier and heavier? And you can see that this set of traces over here, if you look at that red line, that's a ballistic coefficient. That means it's the ratio of how heavy it is to its size. That's pretty equivalent to like the Mars Pathfinder that flew in 97. And you can't really see it probably very well, but this little dot here is the point where it reaches Mach 3. Okay, and you can see that's above, you know, 15 kilometers. And then very shortly, it's, you know, down around Mach 2, and so it's actually, you know, decelerating pretty good in that range. And then you would deploy the parachute somewhere around here. As soon as you get below Mach 2, you could deploy the parachute, and then everything works fine. Well, okay, as payloads got heavier and heavier, and the ballistic coefficient got higher and higher, you start moving out along these trajectories, and you can see that for a mission that was here, the green line, that's more like what Phoenix experienced, you can see that you still have the same basic behavior, but the point at which you reach Mach 3 and Mach 2 is considerably lower. And as you get heavier and heavier ballistic coefficients, eventually you're going to run out of space, you're going to run out of altitude in order to do the parachute deployment and deceleration and so forth. And so that's the fundamental problem. So if you look at this, let's see, I guess this one right here, this kind of magenta thing, whatever color that is, you can see that if you did a perfectly ballistic entry, you just enter and, you know, shove the molecules out of the way and slow down as whatever rate that gives you, you're going Mach 3 at about, you know, 100 meters above the ground. I point that out because that ballistic coefficient is roughly the ballistic coefficient that MSL, the Mars Science Lab, had, and so this is an indication of why they had to do something different. When the ballistic coefficient gets high enough, you can't simply, you know, toss the thing into the top of the atmosphere and stand back and wait for it to slow down, because it won't. So what do? Well, the obvious thing you do is you add some lift. During this hypersonic phase, if you tilt the capsule maybe 10 or 12 degrees relative to the oncoming free stream flow, you actually will generate lift as well as drag. So you're simultaneously slowing down while obtaining a little bit of lift. And it doesn't have to be a lot. And this actually shows the effect of that, where, again, for ballistic coefficients that are sort of equivalent to like Phoenix missions, where you're kind of up in this range, you don't really need to use lift. You can if you want, but as I've shown, you don't need to. When you start getting up into these higher ballistic coefficients, this is where, you know, Red Dragon would be up in this end. As I'm showing, you have to do that, or you would have crashed into the surface. So if you add some of this lift, and in this case, you would basically simply crank in a certain angle of attack at the top of the atmosphere. You would go down and do whatever it does, and whatever it does is this so-called lofted trajectory. You basically, and this was well known back even before we had blunt body theory. You know, Huygens and Sanger worked out things like this, and so what happens is you come down, and as you experience the exponentially more dense layers of the atmosphere, you eventually get to a point where you sort of bounce. You're still actually going at a velocity that's higher than orbital velocity, and so if you're not careful, you could, in theory, skip out. You don't want to do that, but the point is, you're down here now at the low portion, you know, in the lower part of the atmosphere where the density is highest, and so you're scrubbing off velocity while you're doing this. But nevertheless, you come down, you do this little sort of bounce, and it skips out, and eventually you're going to come down. You will eventually decelerate to Mach 3 and lower. And now you can see you're above the ground. That's good. You know, you're not by a lot. You know, maybe 5 kilometers or something. But basically, what this does is that instead of a purely ballistic entry where you basically come in and just, you know, brute force shove the air molecules out of the way, that kind of trajectory, it's all over in about 150 kilometers. From the point of entry to where you're going to either crash or deploy your landing system, it's only like 150 kilometers. You can see that the effect of adding this lift now pushes your downrange to 2,500 kilometers. So really what you're doing, if you want to think of it this way, is you're getting down low and you're flying in a substantially horizontal direction for a long period of time, and that's what allows you to scrub off this velocity over thousands of kilometers instead of hundreds of kilometers. So these this is the analytical work we did that showed that indeed if you use simple lift, you can do it. There's actually a more intelligent way to do it, at least some people, a more complex way. And this is where you actually do active flying. You actually fly the thing down to its terminal conditions. And basically what this shows is this, the blue trace is the trajectory. This red trace is showing the bank angle, the control you're putting in. And what's not, it may not be obvious here, but what's actually happening is when you enter the top of the atmosphere, the lift vector is actually down. Very gutsy maneuver. You actually come in and you flip it inverted and you're actually diving down as fast as you can. Okay, until you get to the sweet spot where you want to be, which is only 10 kilometers or something above the surface, and then you roll the other way. And now the lift vector is up. What that does is that gets you down as fast as possible and keeps you in the dense portion of the atmosphere as long as possible, where you actually have enough lift and drag to be meaningful. And you can see that what that does is that gives you a much flatter trajectory. You don't get that big wild whoop-de-doo. And what that ends up doing is that in the terminal conditions down here, when you're finally running out of control authority, when you're running out of dynamic pressure to do any flying, you're at a lower altitude and lower speed. And what that means is that minimizes the amount of propellant, for example, that you would have to use to do a soft landing. And so one of the things I didn't mention is that because of this high ballistic coefficient that the Dragon capsule would have, you can't really use a parachute system. This is one of the conclusions we came to pretty early on. The current, all the systems we send to Mars now have this supersonic parachute technology that was developed during the Viking program, and it turns out you can only extend it so far in terms of Mach number and size and that sort of thing. And the Dragon capsule is big enough that you can't really use a parachute. A parachute just does not make sense at all. So you're committed to using something else, it'll be propulsion, to do that actual final landing. So this basically marks a break with kind of the Viking heritage means of doing an entry, descent, and landing. By the way, that break with that technology approach is also probably going to be necessary to do human missions. All of the missions that we've done so far, the mission architectures show that you need, to land 40 tons or something. You need to enter like 40 tons on the top of the Mars atmosphere and get it down to support all these human bases and stuff like that. There's no way they're going to use parachutes. So this actually represents a step on the path toward human exploration. Okay, as I mentioned, parachutes are out. And so what we would propose to use is the rockets that are basically built right into the Dragon capsule. As you can see, they're paired up, 4 pairs of 2 that are arranged around the periphery. In the Dragon crew carrying capsule, those are basically put there for the launch abort condition, so that if something goes wrong on the launch when you're on ascent from Earth, you can push the eject button and these rockets will pull you away from the disintegrating stack. hopefully faster than the shock front is following you. And so those rocket thrusters are actually very, very, very capable. They're sized to be able to do that very energetic maneuver that pulls you away from a failing, launch vehicle. And that fact that they're very, very powerful means on Mars, when you're landing, you have a lot of control authority. I mean, it's a hot rod. You could actually pull more G's than you probably want to tolerate. So you probably have to kind of throttle them back from what their normal rating is. But those thrusters, as I showed, this is they're called the Super Dracos, and here's a photo from SpaceX showing that those have been tested and they're under development and seem to work just fine. So then basically once you're down to that last 10 meters, you're descending at a few meters per second and everything is sweet and you land. Okay, so we did the calculations to show how much could you land. Well, there's some subtleties. It turns out that, of course, there's a huge variation from season to season in the Mars atmosphere. There's times you could arrive when it's a thick atmosphere, and there's times you could arrive as a thin atmosphere. And obviously, if you arrive during a thin atmosphere, you're probably not going to be able to land at as high an altitude as you would if it's thick. Just makes sense. It's not a huge effect. It's it's kind of a for a given. If you hold the mass constant, it's kind of like maybe a 500 meter to a kilometer type distance, dynamic range. It turns out that the amount of mass you can land is a very, very linear function of how much you enter. And basically, because that final maneuver is all propulsive, it's just rocket fuel. If you carry more rocket fuel, you can land more payload. It just makes sense. And so that linear relationship holds all the way up to the point where you can't load any more fuel on it, basically, which in our case is roughly around 10 metric tons of entry mass. So the landed mass is a kind of a slow function of that, but basically, if you were to take go anywhere along this curve and take the entry mass and subtract from it the landed mass, you'll get the payload. And for the extreme cases where you enter at around 10 metric tons, you get right around 2 metric tons of useful payload that you can land. That compares, by the way, to the MSL. Currently the biggest thing we've flown. The useful payload inside that is roughly 1 metric ton, about 900 and something kilograms. So it's roughly a factor of 2 improvement over what the current MSL landing system can do, and a lot more usable internal volume, because this thing is, it's a gumdrop shape. It's not a little flat sort of flying saucer shape. Okay, so you got to do a bunch of stuff inside. Basically. What we showed was that if you compare that the landed mass to the entry mass and all that, you discover that the propellant mass fraction is a very constant, 31%. So in other words, in order to do that landing from about Mach 2.5 or so down to the bottom requires a relatively constant propellant mass fraction. That makes sense if you think about it, and that fraction turns out to be about 31%, plus or minus a little bit. So in other words, the roughly 70% of the entry mass that's not propellant is the structure of the capsule itself plus useful payload. But in order to keep that propellant mass fraction relatively constant, around 30% or so, you have to be able to add more propellant tanks inside or not, depending on what total mass you're shooting for. So basically, we looked at making these internal modifications to add propellant tanks as needed to get to the higher landed masses. Then, of course, the Mars ascent vehicle itself. As I said, it's basically a rocket sitting inside of a missile silo. We looked at a lot of different trades on how you would launch that and came to the conclusion that the probably the simplest and best way is to, you basically would have ports in the bottom of the capsule. So after you land, those ports would, be ejected, and so you'd have basically a straight shot of the exhaust plume down to the bottom of the thing. The Mars Ascent Vehicle itself is a full-on high-performance rocket launch vehicle that has to get off the face of Mars and onto another, planetary body, and so it's actually it's a high-performance launch vehicle in its own right. It in the size that we're talking about here, we ended up with masses sort of in the 1,300 kilogram range for the all-up wet mass of that. This Mars Ascent Vehicle, the closest Earth analog we have to it probably is one of these ballistic missile defense interceptors. They're about that size. They have about the same delta V requirement, the same sort of level of complexity. So the community that builds these little interceptors with the little thrusters and all that sort of stuff is probably the same people that you would look to build these things. But nevertheless, we went through the design trade to figure out how to build one of these ascent vehicles. And the first thing you have to do is figure out where it's going to. In a discussion I was having before the talk started, the current decadal survey mission stops in Mars orbit. That's a delta V of about 4 kilometers a second. You have to design a rocket for about a 4 kilometer per second change in velocity to get to Mars orbit. To come all the way back to Earth, it's about 8 kilometers per second total. And so when you think about it, 8 kilometers per second is about the same delta V budget that you would use for a launch vehicle on Earth to get to low Earth orbit. So in other words, if you're going from the Earth up to the space station, it's about that same delta V budget as to come from Mars all the way back to Earth. And there are no single stage to Earth orbit vehicles for a very good reason. The rocket equation pretty much prohibits it. So the task of designing this vehicle is roughly equivalent to designing something that would get from Earth's surface up to to space station. And for that reason, it has to be a minimum of a 2-stage vehicle. And the top stage, it has to be a pretty high performance small spacecraft that's capable of surviving and communicating and doing all the housekeeping things it needs to do on its way from Mars back to Earth. As I said, we ended up with a max weight of around 1,300 kilograms, which leaves roughly 700 kilograms for everything else out of a 2-ton useful payload. I'm skipping over a lot of stuff. We looked at a lot of different propellant combinations. We looked at the possibility of making the propellant in situ on Mars. We looked at cryogenics versus storables and all this sort of stuff, and basically came to the conclusion that the simplest and best is an all-storable bipropellant rocket that you could go out and buy components for tomorrow. So it really requires no technology development. It's an engineering project. You could go and start designing it tomorrow, but no real new technology required. Looked at, again, as I said, transferring samples on the surface. The idea is you'd have this arm that has to be stowed inside the capsule and then comes out and can interface with any kind of surface capability you might have. When you're back in Earth orbit trying to retrieve the sample into a capsule that would come back to Earth, it might look like this. The idea here is you have a retrieving spacecraft has essentially a planetary protection canister on the top of it, and so all you have to do is go out with a manipulator, grab the sample, pull it back into your containment, close the lid, and this, we claim, would break the chain of contact between Mars and Earth, and then basically this retrieving spacecraft would come back to Earth. Some people question as to whether or not that's actually safer than a direct Earth entry, and that argument is beyond the scope of this, but that's to be determined. As I said, this kind of summarizes it. If you look at the estimated capability of the Falcon 9 Heavy to throw stuff to Mars. This is throw weight versus C3. For Mars, the C3 tends to be around here or so, maybe a little bit more. So, but anyway, you should get about 13 tons of throw weight to Mars off the Falcon 9 Heavy. Our the heaviest capsule that we would anticipate is about 10 tons. On top of that, you have to add the service vehicle, or the trunk and the solar arrays and all that stuff, the cruise stage that keeps it alive from Earth to Mars. But even so, we come up with a margin, a launch margin right now of at least 20% of unconstrained, of possibility for growth. Of that, the landed payload breaks out about like this. The Mars ascent vehicle itself can be in the 1,000 kilogram range. All the other stuff like solar arrays and communication gear and all that sort of stuff that you need to stay alive on Mars is contained in that. So there's margin between the Mars ascent vehicle current definition and the mass budget, and then that fits into the launch vehicle mass build up this way, where again we have margin. So the bottom line there is, if you go back to that chart I had where asking the question, does this fit into that? Yes, the answer is yes. It looks like a Falcon 9 Heavy with the ability to land roughly 2 metric tons of useful payload is large enough to start implementing these Mars direct architectures, where you do not have to stop in Mars orbit, come directly back to Earth. So we think that actually it has a high probability or possibility of simplifying the architecture a lot. And I guess I will stop at that point. I guess we got 5 minutes, is that? Okay, I have some backup material.
Just put up your hand if you have a question. I'll get around to you. I'm going to ask the first one, Larry. Is there the opportunity for the rocket to go into Mars orbit if there's unforeseen circumstances or something like that, or is it only is the thing once it's flown once it's shot, is it a ballistic shot, or is there a chance at any stage to intervene in the mission? And particularly with the Top Gun style entry, at what point can you pull out of that?
Well, none. No, if you attempt that the flying maneuvering entry, you're committed to it. Yeah. Now you do have the option if that makes you nervous. I mean, before the mission launches, you could opt for the other approach where you do the lofted entry. The consequence would be more fuel. You'd have less useful payload. It's actually a question though of again, which one is actually less risky. If you look at the human scenarios, where you're actually trying to land 10, 20, 30 metric tons, they also utilize that lifting maneuvering entry. Which you basically need something like that for pinpoint landing. I mean, that's the other side of maneuverability, is it allows you to land close to, but not on, your previously in place capabilities.
And actually Apollo used a semi-lofting trajectory. They went down and came back up again, and so it hasn't been done before. Nice.
Could you talk a little bit about how you modeled the plume shock interaction of the Draco engines during the supersonic deceleration phase, and how high accuracy you think that model is, and what assumptions were made?
Okay, these are the backup charts. So basically, supersonic retropropulsion in 30 seconds. Basically, the whole point, of course, behind blunt body entry dynamics is that you form this strong shock that sits out in front of the face of the entry vehicle, and that strong shock is stable from all the way from entry at Mach 25 all the way down to Mach 3 or something, and in fact that's basically what causes the how you reject heat into the capsule, because it's the main heating is occurring out here. It also of course essentially sort of augments the drag coefficient of the thing. So if you look at these vehicles, they typically have a drag coefficient greater than 1. How is that possible? Well, it's possible because the effective frontal area is actually the area of the shock front, not just the vehicle. Okay, what happens is if you now put a thruster in this scene somewhere, the thruster itself has a supersonic plume associated with it. Okay, there have basically been two types studied. One is you put the thruster right on the center line. Okay. The other approach, which Dragon is using, puts the thrusters on the side. Okay. Now it turns out when 90% of the modeling has assumed the center line thrust, and that basically is kind of a historical artifact from the Viking days, because that's what they looked at. Well, that's irrelevant to our case actually, and it produces qualitatively different results. If you have a center line thruster and you turn it on at a thrust level that's high enough to do some useful work, what you actually do is you kind of punch a hole in this strong shock front. You actually punch a hole in it, you kind of deflate it, and you actually will lose drag that way because of that interaction. It turns out that if you place the thruster peripherally, that doesn't necessarily happen. What happens is at low thrust levels, you're actually inflating that bubble. So you can actually augment the drag by sufficient if you modulate that thrust. However, that's also largely irrelevant for this case because these thrusters operate at such a high thrust coefficient. As I indicated before, these thrusters were designed for the Earth escape, the launch abort case, and they have a huge thrust coefficient. In other words, the amount of thrust produced by these thrusters is at least an order of magnitude greater than the drag produced by the body. And what has been shown is at those conditions, the thruster plumes just blow the thing away. Yes, there's a lot of interesting little dynamics of molecules running around and interacting with each other, but it's kind of irrelevant for the overall body forces on the body. This has actually been shown, by the way, because for the Falcon booster itself, as you know, SpaceX is trying to fly that back and reuse it, right? And they've demonstrated that. Well, in one of their previous flights, they actually demonstrated supersonic retropropulsion with their launch vehicle. They actually turned it around, came back, and fired the thrusters in the rear direction while they were moving at a supersonic velocity. In their case, because those thrusters, they were in an order of magnitude higher than this, right?
Well, but they're also axial. They're not located around the perimeter of the rocket.
True, but the point is that if you get to a high enough thrust coefficient, you basically just swamp out all the other effects. Yes, they're there, they're just not important.
And in fact, when we actually modeled this using post, we actually turned off, threw away the drag terms since they were small, and used only thrust.
So you actually duplicated this work for the configuration.
We wait for the
Okay, okay, well, I'm sorry, okay.
Sorry.
Okay.
Yeah, sorry, Andy.
Okay. I'll talk to you after.
Yeah, we actually modeled, but with the drag turned off and the thrust just at 20 times the drag value. So we eventually just used the brute force approach. We only thrusted for 8 or 9 seconds. Now I've looked at some cases where we actually used the theory as developed by Bakhtian and Optimus and talked to them, and it turns out you use the same amount of propellant, whether you take a kinder and gentler approach or you just blast your way through the shock front.
So, do we use them or not, Larry?
Use
Can
what?
you say whether we're going to turn these on or not?
Oh, absolutely, we're going to turn them on. Okay. Absolutely.
Wow, somewhat different topic. The manned Dragon is designed for about a 2-week endurance in a shirt sleeve environment. You're going to be running this for over 2 years. Are you going to be reducing the operating temperature? And I assume you're powering down the various systems during the cruise phase of the mission. And is that going to require a large amount of redesign of the electronics?
Well, no and yes. No, we're not going to power them down. The assumption has always been that if you're going to use this for a robotic mission to Mars, you basically would strip out all of the stuff that's there for life support. I mean, and in fact, you'd probably run the thing unpressurized. You would, of course, have to put in systems that were, deep space qualified. High reliability flight computers and navigation and comm and all that sort of stuff. All of which you can get off the shelf, of course. And with a mass budget as big as this, there's basically no particular problem with mass or volume to accommodate it. So the assumption is that we would have to make those modifications, and having done that, then everything would obviously have to be qualified for a 10-month cruise instead of 2 weeks.
Larry, that was fascinating. As I recall, when people used to talk about manned flight to Mars, it always was some sort of lifting body device.
Yeah.
How much control do you have here? You're going to have to pick a smooth landing point next to where a cache is.
Mm-hmm.
So what kind of lateral control do you have on this wild flight through the atmosphere?
Andy, did you want to address that? No, I mean, you talked to those guys, right?
The technique is really to modulate that bank angle. So if you want to fly off to the right or the left, you just don't roll 480 degrees like the shuttle did. So you use that same bank angle modulation to get you where you want to go. You want to go shorter, longer, you just modulate your bank angle. You want to go right or left, you do the same thing. We think we could land very close without damaging a rover that's sitting waiting with a cache for us. So, but the technique is basically use that bank angle modulation.
Yeah. So actually, I guess there's two parts to that. One is knowing where you want to fly to, and then the other is the can you fly there. And what we've answered is the yes, you can fly there, because that's exactly what the shuttle does. It uses all these, so you use exactly the same sort of algorithms. The real issue is how accurately do you know where the thing is and where you're going to, and that's basically a function of pre-placed assets. You've looked at your target area from overhead and so forth. So I would say yes. I mean, I think that's the obvious thing is fly to a beacon. I mean, that's.
Yeah, if the rover's alive, it can tell you can figure out where it is pretty well.
Hi, Larry.
Hi.
So the Dragon capsule nowadays, even version 2, has a trunk in the back which operates kind of as a surface equivalent of a service module, although not quite as necessary. Has there been any thought on maybe instead of just chucking the trunk, actually putting it in orbit and using it as an Earth return vehicle? So you would have an intelligent rendezvous with that, and that would return you to Earth.
Well, there's been some thought. We haven't analyzed that particular branch of the architecture tree. A couple things. One is, yes, the trunk has to go essentially all the way to Mars, or it currently does not have any of the propulsion or auto navigation, any of those capabilities to be an autonomous spacecraft. On the other hand, it has a huge volume internally, and there's a huge mass margin, so I don't think there's any doubt that you could do that. I think you could equip it to become essentially an autonomous spacecraft. If you did put it into Mars orbit, now you're stuck with the Mars Orbit Rendezvous part of this again, right? And we're sort of agnostic on that. I mean, the whole idea of doing a direct-to-Earth return is to simplify the parts count and to minimize the number of critical operations. In particular, the Mars Orbit Rendezvous. There's a lot of people who don't, who think that's really kind of risky. So I think ultimately the decision will probably be made not necessarily so much strictly on cost, but on the perceived risk of, where would you rather do these operations, in Mars orbit or Earth orbit, and importantly, the whole planetary protection thing, which we haven't really discussed. There's a huge debate there, and I would say, from what I can tell, you have sort of equal numbers of proponents and opponents. Some people think that a direct Earth return is horribly risky. Other people claim, nope, that's the safest thing you can do. So that argument is still raging, and I can't really say how it's going to come out.
Hi, over here, Larry.
Yeah.
So you segued nicely into my question, which is about the whole planetary protection thing. Is the plan for the level of sterility such that if there are, say, hardy Martian microbes living in the sample, which is, I'm sure, unlikely, but not 0%, that they wouldn't get contaminated by whatever the spaceship brought from Earth that might be really hardy and could survive, vacuum and all of that? Because I know that there's been different levels of that in the different Martian rovers. And I was wondering, for your plan, what that level would be, and for the 2020 rover, what that level would be, since it's dependent on that.
Carol, you might actually be best suited to answer a planetary protection question.
So planetary protection is actually governed by laws and rules. So there's specific requirements for protecting the samples that will be returned to Earth. And those requirements, as far as I know, are dry heat microbial reduction, in other words, sterilization of anything that's going to touch the sample or anything the samples are stored in. The other issue, so that's really about not having a false positive, not having a, essentially bringing something back from Mars and it's really something you brought from Earth in the first place, and misinterpreting it in the analysis. But the other issue in planetary protection is not contaminating Earth inadvertently, right? So not bringing something back from Mars to Earth that gets away and causes the Andromeda strain. And the idea there is that you break the chain of contact. So in other words, you don't let anything that's been on Mars come back to Earth without being in a containment chamber, a containment facility that wasn't ever on Mars. So in other words, that container has got to come from Earth, and it has to be able to survive re-entry in a catastrophic way. So in other words, if everything fails, if everything breaks up, that container still isn't breached.
So it's like a black box on an airplane.
Kind of like that, but did I get it right, Mark?
So that because it's a lander, it would be the most extreme of the category 4 of the planetary protection guidelines. But I wanted to ask the question too. What about the heat on when you're coming in? What are the temperatures that you reach on your shock wave? Because you got to think about forward contamination, what you're bringing from Earth, and then backward. I think that they've figured out a good way to deal with the back if you separate in Earth orbit and break the chain. You can do that just fine. Keep it all contained and make sure that the way you collect it is contained. One of the problems that you, I think, have is that you still are a robotic mission.
Yeah,
so
so you're talking about the forward contamination on the
forward
entry vehicle
contamination, how do you deal with that when you don't have a fairing?
Yeah.
Because typically you clean the outside fairing and then you throw it off when you're
I'm not 100% sure that we wouldn't have a fairing.
Okay.
And we didn't.
Or you can do it with temperature. If you do enough heat on your
yeah.
reentry through friction, you can use that as a way to qualify for reducing microbial burden.
You could have a fairing
That's a non-standard Falcon way of doing it, but you could have it. I would point out that one of the schemes for our human mission is use the dual-use fairing, where you do have that problem with the fairings out there in the Florida sunshine and receiving contamination. So, and the heat going in, by the way, is a lot less than what it is at Earth, which is one of the benefits of operating at Mars.
Two more questions.
Thank you. Also at NASA Ames, they are developing a system that they called ADAPT, adaptive landing system. So I am wondering, is it scalable for this case? Cannot it be used and
Yes, what's being referred to there is this ADEPT. It's an advanced thermal protection material. It's a lightweight carbon cloth-based, as I recall. And absolutely, yes, that is the direction that we were looking when we consider the direct entry, the direct Earth entry option. We would be looking at some kind of technology like that to keep the weight of the thing down so that we could get it there in the first place. That would be probably the leading candidate, I would say. There is an issue, and that is with any of the direct entry schemes, you know, where you're not even stopping in Earth orbit, you just come screaming in. Basically, the probability of a catastrophic, you know, event is driven by the intrinsic reliability of that of the front surface of the entry vehicle, you know. And in previous Mars sample return designs, people have assumed use of essentially the most conservative thermal protection system material available, which is basically the stuff that's used on the front of ballistic, you know, nuclear warheads. The reason being that we have built and tested more of those than anything else, any other type of system. And so the idea there is that that's the one technology where we have a sufficient statistical database that you could make an argument. So the argument is you need to be able to show, you know, one chance in a million of a catastrophic. Well, how do you do that? How do you do that on a system that's only going to work once, right? It has to be statistical. So the current option is use this, you know, highly, very heavy, very clunky, but well-tested material. That leads to a very, very massive entry vehicle that's probably too heavy for us to accommodate. Or you go to something like ADEPT, which is very high performance, you know, very mass efficient, but doesn't have any database, so, you know, no experience base associated with it. So what we're considering is the possibility of a two-level system where the outer surface is maybe an ADEPT-like thing, and the inner portion is an old, well-tested, reliable, you know, conservative material. And the idea being that you would have to have two failures in order for the whole thing to fail. So instead of trying to get your one part in a million in one single system, maybe you do it with a staged system. You know, maybe something like that.
Hi.
Yep.
With the shuttle, a very significant part of the early development was involved with being able to do appropriate energy management in order to have the ability to land with precision. Mm-hmm. And precision is what's going to make this particular mission work or not work. And one of the problems with having a lifting entry is that you have variability in the atmosphere, and you have to have a predictive model that's very good in order to have a Kalman filter that has enough resolution and enough control authority near the end to be able to keep the target adequately within its margins at any given time. How much simulation work have you done in terms of energy management? Have you just done energy budgets, no simulations?
No, that was outside the scope. We're just, first of all, you're absolutely correct. That is the issue. Yeah. We didn't do any of that. We were basically looking at it strictly from a kind of an energetics standpoint. We're just doing the mass and energy balance, you know, to show that it all adds up. The details of that, like how you would actually do that precision navigation, we haven't looked. However, actually some people at JPL have looked at that. They actually took an entry capsule with these kind of characteristics and run it through their MSL codes, you know. I don't actually know the results of that, so I won't. Okay.
Larry,
we
have a blunt body here that you might be able to use in some of your simulations, okay. But I'd recommend not having anyone else around if you're going to try to throw that around. But you might want to use it as well to fill it with coffee or something for those late night excursions into blunt body dynamics.
Okay.
Thanks very much.
Thank you.
Please join me. Thank you.